Given n cities numbered from 0 to n-1 and n-1 roads connecting these cities in one direction, forming a tree, we need to determine the minimum number of roads to be rerouted so that each city can visit city 0. Roads are represented by the connections array, where connections of I, which equals a pair of AI and BI, will represent a road from city AI to city BI. We will traverse the graph and construct two graphs to allow the algorithm to efficiently traverse the road network and determine which roads need to be rerouted to allow access from each city to city 0. This dual graph structure simplifies the identification of incorrect roads and facilitates efficient traversal of the network. Vector of unordered set of type int of graph of n creates an array of unordered set of int with n elements. Each element in the array represents a set of neighboring cities reachable from that city according to the initial direction of the roads. And vector of unordered set of int of reverse graph of n creates an array of unordered set int with n elements. Each element in the array represents a set of neighboring cities reachable from that city according to the reverse direction of the roads. We iterate over the connections array, and for each con, we add city bi of con of 1 to the set of neighbors of city ai of con of 0 in the graph, indicating a road from ai to bi. We also add city ai of con of 0 to the set of neighbors of city bi of con of 1 in a reverse graph, indicating a reverse path from bi to ai. Separating the initial and opposite directions into a graph and a reversed graph allows clear identification of roads that need to be rerouted. After building the graphs, we initialize a counter changes to count the number of roads that need to be reoriented. This will also be the variable in which we will store the final answer from the function. To determine the minimum number of roads that must be rerouted so that each city can reach city 0, we use BFS or breadth first search starting from city 0. As we traverse the graph, we count the roads that need to be reoriented in changes. We build a queue FIFO, first in first out queue, that will be used for the BFS traversal. Elements will be added at the end and fetched from the front. Each city that has been visited is noted in a visited vector of booleans of size n, or the number of cities, initialized with false. This will be used to keep track of cities that have already been visited to avoid repeated processing. The first step is to add city 0 to the queue and mark it as visited. Then, as long as the queue isn't empty, we run a loop to process each city. In each iteration, we extract the element from the front of the queue representing the current city to process. Then, using queue.pop, we remove the first element from the queue. For each neighbor of the current city in the graph, if the neighbor has not been visited, then there is a path from the current city to the neighbor in the wrong direction, away from city 0. We increment the changes counter to reflect that this path needs to be reoriented. We add the neighbor to the queue for further processing and mark it as visited. For each neighbor of the current city in the reverse graph, if the neighbor has not been visited, we add the neighbor to the queue and mark it as visited. This check ensures that we can access all cities that can reach the current city, facilitating the traversal of the entire road network. At the end of the traversal, we return changes, which is the minimum number of roads that must be rerouted to allow access to city 0 from all other cities. In conclusion, we use the graph traversal approach combined with checking the initial direction of the roads and the opposite direction. By constructing an initial graph and a reversed graph and traversing them using BFS, we can determine the minimum number of roads that must be rerouted to allow access to city 0 from all other cities. The counting of the roads that need to be reoriented is done efficiently during the traversal, ensuring an optimal result. This algorithm is efficient and performs well due to the use of DFS traversal, which provides a complete view of all connections in the graph and correctly identifies the paths that need to be rerouted. Now, it's time to test this code and ensure it works correctly. Feel free to experiment with your own ideas, test edge cases, and explore alternative implementation. This not only helps verify the solution, but also enhances your learning and problem-solving skills.